Okay, I will begin by writing down a two-digit solution to this number theoretic equation. N equals 77. Turns out to be a solution, and we'll write down why that's the case. But notice this is an example of what they call a semi-prime. 7 times 11 is 77. 7 and 11 are both primes. So this is called a semi-prime number. Now, any semi-prime number is going to have 4 divisors, namely 1, the 2 primes, and the product of the primes. So the 4 divisors of n would be 1, 7, 11, and 77. Okay, so what that's going to lead to right here would be 4 squared. Okay, right here again, there's 4 divisors, so there's a 4 that goes here where d of n is for n equals 77. Now the sum is not too difficult. We can write that down as 1 plus 7 plus 11 plus 77. Okay, and I'll just put this parenthetically, just hopefully for legibility. Now it's pretty easy to verify that when you subtract 12 from these two numbers, you get 0. 112, excuse me. You get 0. Okay, again, folks, 77 plus 11 is what? 88. 88 plus 7 is 95, and 95 plus 1 is 96. So you have 16 plus 96, which is 112. And of course, when you subtract 112 from itself, you get 0. So n equals 77 is a 2-digit solution. We're seeking a 3-digit solution. So let's get busy setting up on how to do that. Now, this comment here that n cannot have too many divisors, that's kind of vague, but notice that the 112 produces kind of a constraint on how large sigma of n can be. And it's going to grow pretty fast, right? You're adding up all the divisors, including the number itself. It's going to grow pretty fast, so you can't pick a super large n, okay? So let's take a look at a little bit of machinery that will make this problem a little bit easier. As usual, on many number theory problems, you look at the prime numbers, and you can almost define a prime p to be any number that has 2 divisors. Okay, that's what a prime number is. Like, for example, 13. The only divisors of 13 are 1 and 13. The only divisors of 19 are 1 and 19. So we can actually define a prime number using the number of divisors functions, and we get 2. Okay. Now the sum of the divisors is even easier. Well, it's about the same. The 2 divisors are 1 and p. So the sum of the divisors, let me erase that. The sum of the divisors, let's write it just adjacent here. Okay, the sum of the divisors for any prime p is just the prime number in itself, in 1, so this is going to be p plus 1. And this is about as simple as it gets as far as these two number theoretic functions, the sum of the divisors and the number of the divisors. This reads p plus 1, folks. Okay, p plus 1. So that gives us a nice sort of check on this problem here. If you put, if you use if you're considering a prime number, this is going to become 4, right? D at p is 2, and then 2 squared is 4. And then right here, you're going to have plus p plus 1. And this just becomes a very simple linear equation. Minus 112 is equal to 0. And so really you can kind of forget that the letter p is there. But you'll notice quickly that this would be the same thing as saying p is equal to. At this point, we have no assurance that the actual number we get when we solve this will be a prime number. We're just using the letter P symbolically here. Okay, so you have P. Now what's all this stuff add up to? This is minus 111 plus 4 is minus 107. Bring it to the other side, and indeed you get a prime number. But as far as the problem goes, this constant could have been something that would have forced this to be a composite number. But anyway, P 107, it's easy to verify that 107 is prime. Okay. You can check all the divisors less than or equal to the square root of 107. You got 2, it's not divisible by 2, 3, 107 is not divisible by 3, 107 is not divisible by 5. It takes a little bit of time to verify that 107 is not divisible by 7, but you know 7 times 12, 7 times 13, 7 times 14, 7 times 15 misses 107, right? Okay, so 7 is not a divisor, and certainly 11 is not a divisor, which is actually greater than the square root of 107. Okay, so we do get that 107 is prime, and it's a 3-digit solution. Okay, so that takes care of it right there, folks. That is our answer. Notice I didn't get too specific. I says, can you find any 3-digit positive integer solutions? Well, I found one, and I can't really prove that there are not any others. I kind of think this is the only 3-digit. But I could be wrong, but I was careful about the way I did the instructions here. We found a 3-digit positive integer solution. You guys, let me know if you can find any others. I think the size of this constant kind of minimizes the possibilities of finding anything larger than 107. Just intuitively, that's how I feel. But what I've done here certainly isn't a rigorous proof. Okay, and it turns out up here that these semi-primes, another solution to this as far as 2 digits would be n equals 3 times 23. And you guys can verify that. And there's, I think, one other. 2 times 31 maybe even is a solution. Okay, but there's a cool way to get that just based on kind of an enumeration using some other formulas. But this is also a solution. We've shown that this is a solution. And so far, this is the only 3-digit solution I know to this number theoretic equation. All right. Thanks for being.